What assumptions make analysis of fluid flow easy? Well, for one thing, laminar flow tends to be easiest. So having well-defined flow lines makes things easy. So we're going to say laminar flow is good. Now, laminar flow tends to happen when there's viscosity, but it turns out viscosity is not really the easiest thing to deal with. It's possible to deal with, but it can complicate things a little bit. So if you can get rid of viscosity too, that'll make things even easier. Although how realistic that is in all situations is a bit questionable, since generally viscosity tends to cause laminar flow, and yet we just said laminar flow is easy. Now, if we look at some more of this list here, the turbulent flow included random vortices, and vortices represent rotational type of motion. And so having rotational motion, or you could say the angular momentum associated with that, that tends to make the analysis of fluid flow harder. So another assumption that's maybe good to make for making the analysis easy would be to assume zero angular momentum, or in other words, no rotation, an irrotational fluid. A final thing that could make things, like if you have, in that sense, all four of the things I think I'm going to wind up, I've listed three so far. Here's a fourth one, is if the fluid is incompressible, because then you can assume that the density is the same throughout, and that always makes things a little bit easier. Now, does that necessarily mean that we can make all of those assumptions in every single situation? The answer is no, and there are definitely situations that make maybe just one or two of those assumptions and are still, it's still possible to analyze them. In this class, I'm going to try to focus a little bit more on situations, just to keep things simple, since we're just doing one chapter on this. We're going to mainly look at situations where all four of the assumptions I just listed. Let's go and look at the answer. We can see them listed, right? So it was non-viscous, laminar, which I kind of already mentioned. Those may in reality not really happen together, but we're going to assume that it can anyways. Maybe one way of saying is that in reality there'd have to be viscosity, but in some cases, for certain kinds of flow, it's maybe okay to ignore that viscosity and recognize that the main impact it has is negligible. And one of the reasons why that is it tends to have an impact, especially like in flow through a pipe, more on the flow near the edge of it and less in the middle of it. And so, although it is nice to take that into account, it's certainly easier if you don't have to. And then we said the incompressible, which it's actually not the worst to have a compressible fluid. It just means you're going to have to deal with the effects of possible changes in density, which can have other effects. We're going to, in the next topic, we're going to look at the Bernoulli equation, which assumes incompressibility, assumes laminar flow. It's actually based on energy conservation. So in that sense, it tacitly assumes that there's no viscosity, because that really viscosity is like friction, which would spoil mechanical, I should have said mechanical energy conservation to be specific. So again, those are the kind of things we'll be assuming. And it actually also assumes the irrotational part. So all four of these assumptions are going to wind up needing to be there in the next topic. And the amazing thing, though, is that result is able to make predictions even in situations where maybe one or more of these assumptions is not quite 100% true in reality, and yet it will still tell us what happens.